And these are, as I said, very useful to keep in mind. These are correspondences or mappings to different models, and mappings, as I emphasize, work both ways. I mean, you have your favorite problem, say KPZ, and it maps onto something quite different, Berger's equation, or, which describes a moving fluid. The intuition goes both ways, and you can hope to learn quite a lot about KPZ, let's say from this mapping, as much as you would learn about the other system from the KPZ equation, and similarly the lattice models as well. Okay, maybe we quickly run through these one at a time so that we know where we are. Problem 1 had to do with the mapping between configurations of your exclusion process, whether symmetric or asymmetric, a configuration, to a configuration of links which we imagine represent an interface in this way. And as we saw, the dynamics of particle hopping, which is the elementary move in the particle system, corresponds to an elementary move which either sends a local hill into a local valley or a local valley into a local hill. Again, depending on the rates of the exclusion process, whether they are symmetric or asymmetric, this would have been symmetric or asymmetric. So this was something that is in the literature called the single step model. It's a model of a moving or fluctuating interface, and good. One immediate thing we saw, in view of this correspondence, was that we could work out the height correlation function very trivially in this model. And just to remind you, what we found is that the height correlation functions at equal time, that grows like r. The mean squared grows like r, so the RMS grows like r to the 1/2, which means that the roughening exponent in this problem is a half. So that came out very easily because of the correspondence to the particle model, where we had already proved product measure. This was another correspondence, and this had to do with bunches of particles, 2 at a time, being deposited or evaporated from the system here. And as we saw, this is an exact correspondence to the symmetric exclusion process. So with equal rates they are coming in. If they are unequal rates, it's an interesting problem to find out exactly what the corresponding exclusion process is. You should work that out. And this works not okay. I should emphasize that this correspondence holds only in one dimension, and the reason was, as we said, that this has to do with the way of defining height. I mean, if you define the height difference between 2 points, and if you're thinking about integrating over the density between those 2 points, well, there are multiple paths in higher dimensions, and you may not get the same answer. You can't do this mapping. So this works only in one dimension. This other correspondence works in any dimension, provided you have a bipartite lattice, where you can make this transformation from the A sublattice to the A sublattice, and from the B sublattice, particles going to holes as you make the transformation. Okay, so this was supposed to be a quick reminder of what it was. Number 3, I think I have not mentioned, but it's important to say, and that is if you have the Ising model. So you remember the Hamiltonian for the Ising model. Let's say nearest neighbor interactions. This is the energy, but now you can ask for what is the kinetics of the Ising model. And you can define different sort of kinetics depending on the physical situation. You could define, for instance, if you have a lattice, you can think of spins. So this is your Ising configuration, and you could think of either, well, several types of kinetic moves. Of course, we would insist that these obey detailed balance, because they in the equilibrium steady state, because you want to describe an Ising model in equilibrium. But kinetic moves, what are they? Well, you can think of 2 things. One is that you could think of taking a single spin and flipping it, and doing this randomly, in a way, designing your rates such that you are sure that you will respect detailed balance in the steady state. That's possible to do. Glauber did it to start with. The other possible move that you might think of is spin exchange. Okay, this is known as the Kawasaki dynamics for the Ising model, and what it says is that if you have an upspin and a downspin, you will interchange them. Okay, whether you actually interchange them or not, you will decide by, as a function of the rates, which in turn depend on Boltzmann weights and so on. Okay, so these are the two sorts of dynamics which are studied for the Ising model. All I wanted to point out is that at infinite temperature, okay, when the energy difference between different configurations is of no consequence, in that case, this conserved spin exchange dynamics reduces to the exclusion process, because you can associate an upspin with the particle, a downspin with the hole, and this exchange of up and down would be just a particle hop to the hole. And therefore, there is a one-to-one mapping clearly between spins and particle configurations, and also a one-to-one mapping therefore between spin exchange and particle hops. So, T equal to infinity Kawasaki dynamics in any dimension anywhere will be described by the symmetric exclusion process over on that lattice. Okay, perhaps I should have mentioned here in a way, this is also a correspondence for how does the exclusion process map onto the problems that Professor Chaudhary has been talking about, namely the larger objects on a lattice which move by one lattice spacing, but which are large. I mean, they could involve k. So, let me call it Kramer exclusion process. So, the picture that goes with that is of course that we have a lattice and we have objects which are k sites long. Here k is equal to 3 for instance, and you have several of them. A finite density of them on the line, and let us say we specify a rule, either they diffuse or perhaps they move only forward or backward with different rates. I mean, some rule you can specify. What can we say about this problem? This problem, as we see, is of great interest in many situations, especially in the context of traffic and molecular motors of various types. Well, so how will we attack such a problem? Again, try to make a mapping between configurations of this and configurations of the ASEP. How would you do that? Given a configuration here, you can define a smaller lattice with fewer sites. If you had L sites here, you will have L minus total, well, some formula, k minus 1 times a number of kmers, L minus this, call this L prime. So, define a new lattice on which these 3 points are shrunk to 1. Keep the holes as they are, etc. So, you will agree that there is a one-to-one mapping between configurations. How do I go from here to there? I knock out the 2 right hand particles in each kmer, and I can then construct an exclusion process here. It's a little tricky. I mean, so at least this mapping is there, 1-to-1. And given this, I can reconstruct that because I just add 2 particles on the side. What is tricky is that the location here will depend on the the x coordinate here will depend on how many, given a configuration here, there is a little trickiness in the location coordinate, because that will depend on the number of kmers before that, but does not matter. But we can use this sort of correspondence quickly to figure out the fundamental diagram, And I'll leave this to you as an exercise. Do this correspondence, work it out. Let me write down the answer. So in the Kramer problem, the answer for the j as a function of rho is, if I have it right, p minus q or u minus v, maybe we should say. Times rho times 1 minus rho divided by rho plus k into 1 minus rho. Verify this. And you can work out also the location of the maximum of j versus rho. So I'll write down the answer for that. So the maximum occurs at rho c equal to, again if this is correct, root k over root k plus 1, where k is the length of the object. So minimum check we should do is k equal to 1, because we know the answer. So get 1 over 1 plus 1, which is 1 over 2, which is half, which is the right answer. For k equal to 2, we can work out some answer, but think about k very large. So for k very large, this approaches 1. So the maximum shifts right, and you can work it out for each k, and the curve therefore looks like that. I mean, distorted, and gets more and more and more distorted. And there are many other things you can work out. You can work out density correlation functions, which in this case show an interesting periodic structure having to do with the fact that you have Kramers. I mean, so given a particle somewhere, it's very likely that the next object is next site is also occupied by a particle, because these are big. And there's a very interesting sawtooth structure in the correlations. Even dynamics, you can make some correspondences and you can work things out. Okay, so I will leave this at that. Coming to the other sort of problem that we have begun to discuss, namely the KPZ problem. Again, there are various correspondences and mappings, some of which we have not done today, but we will. Not done yesterday, but we'll do today. And one is, of course, to the general class of driven diffusive systems, but that we have already seen. The exclusion, asymmetric exclusion process is indeed a driven diffusive. So in dimension 1, we have seen an example of that through the lattice model. And as we saw, by making the correspondence dH by dx being the fluctuation in density, the KPZ equation here could be mapped onto the continuity equation with a noisy contribution to the current, where we expand it to some order. So we'll call this I don't know what to call it, but that expansion. So a driven system current fluctuations. You know the expansion I mean. We wrote the continuity equation and then expanded that in terms of rho. Do you all remember? Yes? No? Can anybody say no? Then I'll do it. I mean, okay, we'll look back in your notes. I mean, what I mean is we wrote the continuity equation d rho by dt plus dj by dx equal to 0, and then we expanded j as j systematic plus j diffusive plus j noise, etc., etc., that development. Okay, so that mapped onto KPZ as well. But as we will show today, KPZ also maps onto other problems. One is a problem in fluid mechanics, Berger's equation with noise, and the other one is something to do with directed polymers, which I will define, and it's worth knowing this. So these correspondences are actually discussed in the paper by Medina et al., which I gave you a reference for. It was Physical Review A after all. It was not Physical Review E, Physical Review A, 1989. If you want the page number also, we can give it to you, but nowadays it's easy to find that, so I won't do that. Okay, good. So these are the sorts of mappings we have been talking about, and we will come back to these. Now, the other thing I want to do besides the mappings and discussion of KPZ in general is the problem that Debashish Chaudhary referred to, namely the problem of the open asymmetric exclusion process, where you specify input and output rates alpha and beta. And interestingly, that problem has phase transitions. So, the steady state shows phase transitions between different sorts of states. So, that is the other thing I would like to work out. Now, the question is, in which order shall I do it? Maybe let us do the ASAP with injection and removal, and we will come back to these further discussion of KPZ, especially the burgers is very interesting, because in the fluid context an invariance, namely Galilean invariance, which we take for granted in the fluid context, has a very non-trivial consequence for KPZ. So, this is the advantage of mappings. We will come back to that. But for the moment, let me address this problem of the asymmetric exclusion process with injection. In fact, we will consider the totally asymmetric exclusion process, which justifies the use of the T in front of the ASAP. This was defined by Mr. Chaudhary, and okay. So, let us draw a picture first, just to get clear what it is that we are talking about. And what we are talking about is our usual lattice, except that we have not periodic boundary conditions, but we have injection and removal. So, we have injection at rate alpha, we still have exclusion. So, for instance, something is attempted to be put here on the first site with rate alpha as opposed to some other rate, but it will succeed only if the particle is, if the site is empty. Okay? So, exclusion is there. Everywhere else, let us say the rate is 1 in the bulk, except when we reach the end. So, for instance, this can move here with rate 1 and that can move there with rate 1, and of course, if this tries to move here, it actually can't move because this is blocked, the usual exclusion process. But this can leave at rate beta. In other words, if there is a particle here, it will hop out with a certain rate beta. And we want to know what happens as we vary alpha and beta. Okay. Now, suppose alpha and beta are equal and some value like 1. Well, in that case, we do not expect much of a change qualitatively from periodic boundary conditions, although the total number will not be conserved, it does not matter. But by and large, the system will carry a current as it did in the periodic case, right? Because something is, it comes and goes. But now, suppose we fiddle around with these parameters, and suppose we make, for instance, beta very, very small. The height of smallness would be to make it 0. But if you make it 0, then you come back with the problem some of you were there in the tutorial, and those some of you know what that problem is, and you also know how to solve it, and that is the solution with walls. So, that was actually I felt an instructive exercise that we went through. For those of you who are not there, please ask your friends and try to catch up. But let us suppose beta is not 0, but small. Okay. So, there is a small probability, let us say 5% of something leaving, whereas well, what will happen? So what do you think will happen? So every 20 steps roughly something can leave. But in the meantime, what about the other 19 steps? It is not able to leave because there is no call, but things are coming from the left. So things will pile up, and it's possible that they will pile up to a macroscopic length, in which case one would have two distinct regions in space, macroscopic space, and you would say you have actually a macroscopic traffic jam or phase separation, or some sort of not phase separation, but you have a very high density built up somehow. And indeed, and that would be qualitatively different from a phase in which you have more or less uniform density. Okay, so I am just trying to argue that you expect phase transitions in this system. But now how can we tackle this problem? So this is actually the first paper to, I think it's one of the first, if not the first, is there's a paper by Derrida, Domani, and somebody you know well from last week, David Mukamel, in Journal of Statistical Physics. Again, let me not give you the precise reference, 1992. And they've done a couple of things in the paper. One is they've solved the problem exactly. We will not attempt to do that here. We could, but it will take time, and we don't have time. Instead, we will adopt an approximation. Now, just general philosophy, is it good to do approximations? The answer is yes. I mean, the answer is yes, but you should examine the approximations, and you should also get a feeling of how valid or not valid it is in various situations. But there's nothing wrong with approximations. Make approximations and make them slightly boldly, and but equally critically examine them, in the end. One approximation that you all have all heard of, I think, is the mean field approximation, right, in the context of equilibrium statistical mechanics. And there was a school of thought, especially in the 1970s, which said mean field is pretty bad. But given what you are getting out for what you are putting in, it's really very good. And much of the modern theory of critical phenomena, namely the epsilon expansion, etc., is an expansion around mean field theory. So approximations are not bad. In fact, what we are going to do is a mean field approximation in this model. What will mean field mean? It will mean in this context simply that if I have correlation functions ni and j, I am going to approximate this by ni and j. Okay. Unlike equilibrium statistical mechanics, where there is a good variational derivation of the mean field theory and justification as a, in terms of the Bogoliubov inequality, here there is no such justification, but it's a working approximation, and it's a good working approximation. So we will do it without apology. Okay, so this is the mean field approximation. As you will see, it's still not a trivial thing to do, because although we have done this decoupling, the ni's are not the same from I to I. We don't have translational invariance. We have injection at H alpha. So the the ni, average ni at site I, is certainly going to depend on I. That is something we cannot get rid of. Also, we want to solve this problem right now, and maybe as far as we are concerned only in steady state. And in that, of course, gives you the simplifications of steady state, including the fact that the current is strictly uniform. The steady state current is the same from this bond to that, although the average densities are different. You all remember this. I've emphasized it. Professor Chaudhary also has mentioned it, and we are going to use this point. Okay, so let me use some notation to be consistent with these authors, namely little ti is the average of ni. Why ti? There's some reason in the paper, but we will just adopt it. I just want to use the same notation. Okay, in that case, what is the current? Well, let's write the current in the bulk. What is it? Well, remember, things move only forward. So the correct answer would have been ni into 1 minus Ni plus 1. Agreed? Because you want both to be this full and that empty. But now we are going to factorize this by this assumption, and we can write this therefore as Ti into 1 minus Ti plus 1. There is nothing in front because we are assuming the rate is 1. I mean, we are dividing out, we are expressing the current in terms of that rate. Let us call the current not J as we usually do, but again sticking to the notation of that paper, let me call it C, C for current. So then, you see I have a system of equations, right? So this holds for each I. For instance, I mean, yeah. So I mean, I can write this for I minus 1 to I also, I mean, if I wanted to. So this is equal to Ti minus 1 to 1 minus Ti, etc., etc., etc. Only let us write the equations for the first and last sites a little carefully, and they are T1. So this is equal to, okay, let me write it separately here, T1 minus T1 T2. Okay, that is of course the normal equation, but that is equal to alpha times 1 minus T1, and that is equal to the current. Agreed? I mean, this is the normal formula, alpha because that is the rate in, or if you like, if you imagine something there with probability alpha, then this would be the rate in. And on the last site we will have Tn minus 1 minus Tn into Tn minus 1 equal to beta Tn equal to C. Okay. Now the way we will view this, okay, so what do we have? You have n equations and you have n unknowns. The only problem is these are nonlinear equations. So we can't just say, okay, I'll use matrices. You can't. Matrices work for linear problems. Okay, so what will we do instead? We'll realize that what we actually have is a recursion relation on our hands. For instance, you can cast that equation, you can solve that I plus 1 equation wherever it is in terms of, you can write assuming that you know the current. Suppose we say the current is C, whatever it is. So then this is 1 minus C over Ti. And the reason we do that, of course, is the C is not depending on I, it is the same C everywhere. So in principle, what should we do? Well, so you take a T here and you determine that and you determine that and you determine that and so on, and you can determine everything down the range. So if you started with T1, you know, somehow, suppose you knew C and you wrote it as, you know, you solve this equation for T1, put in T1, and then you iterate. I mean, you're all very familiar with computers, so you can easily iterate and you can get some equation for Tn, but then Tn had better match this boundary, I mean this condition on the other side with the same C and the given beta. And most likely your initial guess would have been wrong, so you tune that until you get it right, and if you've done that, you've gotten the full profile. Okay, so this is the way you could do it. But in fact, we can proceed a little better than trying out one by one on a computer. Trying out one by one on a computer has its great advantages also. Do it and you will find how nicely you have to tune T1 in order to reach the target Tn. So try it. I mean, this is quite a lot of fun to do. Take n equal to 20, good enough, and just play around with this with alpha and beta. But how can we do some analysis without causing to actual iteration? And whenever you have recursion relations, let's say here you have one, first thing you should do is look for fixed points. Fixed points are what? Take a trial value of t, call it t star, such that when you plug in here, you get the same t star there. Is it possible? Well, it's possible because you can write you can postulate a T star, you can write that equation and solve for it and see if you get a solution. So we do that. So when you do that, you have a quadratic equation for T star. So here are the fixed points. What are they? So here, in fact, we'll just call them T plus or minus because there are two roots of the quadratic. And so they are, the two roots are given by half. So the solutions are half, 1 plus or minus square root of, well, let me write it as 1 minus 4c to the half. This is the answer. So this immediately tells you there's some range of c which is sort of sensible, which is c less than a quarter. By the way, remember the quarter was the maximum current we had in that periodic boundary condition case, because it was J was something times rho times 1 minus rho, and it was largest, that was a quarter. So fortunately, we are at least talking about smaller currents, because otherwise this root will become imaginary and then we would not know what it means. Now, how do you use fixed points and that notion in recursions? So this is the way you do it. So let me put up a picture here. Well, what I'll do is I'll plot the right hand side. Okay. Okay. So what is the idea? We input a certain value of t, ti. We take this function. So we may as well draw the function. So let me draw it. So it looks like this. This diverges as ti goes to 0 with a negative. So this is that negative infinity there coming in, but it's a curve of this sort. Maybe I didn't draw it well enough, so let me move this a little closer. Okay. Okay, this is a little distracting. Okay, let me redraw it. Okay. Okay. Also, for good measure, let me draw the line. This is x and that is y equal to x, which is a simple straight line, 45-degree slope, and let me put it in yellow. Here it is. So suppose I have this. What is special about these two intersections? These are the fixed points, right? So we'll call this t plus and this t minus. Here they are. I mean, we actually found the formula for them, but they're here. Now, how do you use these curves? Well, it's very simple. This is what? This is the ti. This is ti plus 1. What we have to do is we have to imagine a ti. Let's imagine a ti. Okay? See here, let's imagine this ti. Okay? Now, how can I find ti plus 1? This is t minus. Let's move it out. So given x, how do you find y? Well, so x, you just go left here. This is the point. Would you, have I done it right? No, wrong. Take it back, rub it out. Here's x, here's the y corresponding to that x. Right now? Yeah. So given ti, this is ti plus 1. I want to go to ti plus 2. So what do? But I don't want to write ti plus 1. I'll just push this here. This is the next ti. Agreed? Now what do? I just go up back here. Ti plus 2. How do I find ti plus 3? Do this, do that, do that, do that, do that, do that. Okay, I'm doing something for a long time. Will I ever finish? Suppose I take 1 second to draw each of these. Up, down. I'll do half second. Then I'll do the next half second. How long will I take to reach this point? Yeah, infinitely long. Why does it have to be infinite? Because if it were finite, I would have reached that fixed point, and then I would have been there forever. That doesn't happen. I mean, you can check. It just takes infinitely long to reach. But now your system fortunately is not infinitely long. It's quite long. It's L long. L is not infinite. But assuming L is big, you will have reached very close to the fixed point. Okay. However, look at it. We started here. This is a nice plausible value of Ti. How many iterations did it do? 1, 2, 3, 4, 5. Okay, after that, okay, maybe 6. You have sharp eyes. You can see number 6. After that, I can't see anything. It's practically T plus. It's not exactly T plus, but it's practically T plus and getting closer and closer and closer to T plus. So it means, translated into your lattice, is that the first 5 sites will have some variation, noticeable variation of the density, and then it will be just constant. So this is the use of such a picture to translate back to density. Have you all understood, everybody? Okay. So this is the way. I mean, these are actual densities and you can translate them. So for instance, if you translated this, what would you get? You would get a picture like this for T versus what are we calling it? I, going from 1 to, let's say, capital N or L or whatever. Well, so there's a variation of some sort, and then it just goes there. Actually, your T is increasing, no? So, okay, let's say it goes this way. And this value that it approaches is T plus. So here on the T axis, you have T plus. You could also, for good measure, write down, since you know it's special, T minus, but you're drawn into T plus in this way. So far, so good? Now, okay, you can actually figure out then by setting the two. Okay, we'll come back to how to actually figure out the value of C, etc. It's simple to do. But this is one scenario. Scenario which says that you actually have, okay, let's put down the density profile, quite a high density. Notice that T plus is bigger than half. Is that obvious or not? It is, because there's a plus sign after half. So this is the way the curve goes. But there was another fixed point here, T minus. So suppose I had started at T minus, what would have happened? Louder? You will remain there. It's a fixed point, so you will stay there. Okay. So suppose I start from T plus 10 to the minus 10. What will happen then? Somebody said, not quite. Some minuscule movement and then movement. So, depending on how close I start to T minus, although it is unstable, you will go away to there. You're on top of a hill. By being very close to the top, you can stay very, very, very long near the top of the hill. How long? You don't. It's not even infinite. It's just L sites. So you can adjust where you are quite well, and you will be close to T minus. So what is the alternative scenario? The alternative scenario is that, well, sorry, but you started here, very close to T minus, and then, okay, I mean, at some point you'll go elsewhere. So you perhaps, towards the end you'll deviate from that and go somewhere. You may not even reach T plus, because this might be the end, So you see the density profiles are very different. This is a high density. This is a low density. Low density where? In almost the full system except for 5, 6 sites. High density again except for the first 5, 6 sites. So, you get the point, right. So, if you like you can try to, you know, on a separate plot try to see what happens as you fiddle around with these parameters, and you will be able to see that there are just a few steps in the bulk. Yeah. Yeah. I couldn't hear. Further towards the right here, you mean? Well, the argument was that if you start here, within 6 steps you are very close to T plus. So, okay, sorry. So, you are never actually at T plus, and I shouldn't have drawn it this severely. So, you are approaching T plus quite fast, simply because you are making an infinite number of steps. Sorry? Middle where? Middle of the lattice? I am not assuming, I am saying it has to be, because to go from here to T plus requires an infinite number of steps. No, no. Okay, assuming that I have started here. Okay. If you start here, that is a good thing to try. You will quickly find that you make some 5 steps here. I mean, let us see one, if you like you can do it, and then you will spend most of your time near T plus on the other side, which would be an approach to T plus from this side. So, T plus just draws everything in. So, if you like, if you want to put arrows, put an arrow here and an arrow here. This is a stable fixed point. Whether you start from top or bottom does not matter. You are drawn into T plus, and most of the time you are T plus, but you are never actually at T plus. But you are close enough to T plus to arbitrary accuracy, I mean depending on L. Okay. Similarly, here you could have started with something here, and that would have led there also. So, you work this out. But this is assuming that you have these 2 distinct fixed points T plus and T minus. There is a third possibility as you change parameters, namely C, maybe this curve will just graze this line tangent, in which case the 2 roots will have coincided, and you will have an interesting scenario. So, here is your line, and this curve is almost, if not quite, touching that, arbitrarily close. Then you can show quite easily that, for instance, if you start with a point here, what will happen is that you will do your usual sort of thing, no? You will go here. Oh, sorry, you have to go here, and then there, and then there, and then there, and then there, and there. Now you are very close to a fixed point in this scenario. So, what will happen is you spend a lot of time here. Eventually, you might emerge, and then what will happen? So, you will be here, go there, go there, go there, go there. But in your L steps, you would have spent practically all, not all, but practically all in this neighborhood. Okay, so I am just pointing out the 2 scenarios. Now, what you have to do is you have to sit down, and this bit of the algebra I will just illustrate in one of the phases, because it will just take too long to do otherwise, and translate this on to conditions on alpha and beta. See, physically you expect the high density phase to happen if beta is small, I mean as we argued right in the beginning. In fact, these things will come out from the equations with, so how would you do it? For instance, T plus, let us look at this high density phase. Tn is practically T plus. Okay, so you can solve for T plus in terms of C by beta. On the other hand, you know that T plus is bigger than a half. Therefore, C by beta, there is a restriction on C by beta. The same C enters on the other side. Where is that alpha? Here. That will imply another restriction on alpha. Put everything together, and there is a bit of logic you have to use, which I will not get into, to figure out what happens. To summarize, what happens is you get the phase diagram that Devashish had put down. Okay? So, let me just put the phase diagram down and ask you to verify this, if you like, with the help of the paper by Derrida, Domani and Mukammal. They have worked out the mean field theory as well in precisely this way. They have actually worked out the exact solution and then the mean field solution. See, that gives credence to my saying the mean field approximation is a worthwhile approximation. Somebody who solves something exactly, why would he bother to do mean field? Because mean field can be done anywhere in any circumstance. Sometimes exact solutions need very exact, models to be able to solve. But this you can use in many, many situations, and realizing what the pitfalls are, you go ahead and do it. It gives you good, sensible answers. In fact, it gives you the exact phase diagram in the alphabet, it turns out. How do we know? That's because they have the exact solution, you can compare. That gives you some confidence in the mean field theory. I will also tell you in the end what it does not get right. It is okay. So, you learn and you see what you can do about that. Okay, good. So, let me do it this way. Yeah, I mean, you had already shown it, right? But let me put it down anyway. So, here is beta, here is alpha, and here is the phase diagram. So, there is a nice 1/4 of this thing laid out. Now, whenever I see this, I am reminded of a puzzle that I was given as a child. Let me pose it to you all. You all solve it in your spare time. One sec. Okay, there is a farmer. Sorry for the digression. Farmer has, was it 3 or 4 children? I think it's 4. I mean, I can do the drawing and find out. He has 4 children, and he has this big field, except there is a house here. Now, the remainder of the field is to be divided equally amongst the 4 children. Equally does not mean only equal area. It means equal shape, the same shape, rotations allowed. Okay? So, find a division of this remaining thing amongst 4, the 4 children, which will satisfy this. Anybody who does this before the class is over will be castigated, because you are supposed to pay attention. You can do this later. Okay. Huh? Yeah, you can't leave out anything. Yeah, otherwise you can just put right. Okay. But our business today is not to solve puzzles. I mean, actually it is, but other puzzles. Okay. So, here, remember the convention I told you all? What color is phase coexistence? Green. So, here. Joshi, is it fair to call this a critical phase? The maximal current? I think we can. It's a large fluctuation phase. So, we can color it red. This is what I wanted to do. Okay. This is not a very good red. Okay. Okay. So, this is a critical phase. This is low beta, so beta less than alpha is here below this 45-degree line. So, this is the high density phase. Conversely, alpha going to beta, beta going to alpha, and particles going to holes will give you a reflection, and that is the low density phase. And this is why this line which runs across is at 45 degrees. If you break particle hole symmetry, this will not be true. And here is a coexisting phase. where if you like, so let me just draw the profiles that correspond to these. So low density, okay, so maybe I'll just reproduce it here. We'll just draw the green curve again. So except near the end, it's at T minus. So this is the low density phase. High density phase, except near the end, near the, except near the beginning, it's at high density throughout. And the other one, this phase coexistence, would be what you would expect. It's low density and high density coexisting. Now, do you know which order? I suppose it's low density here and high density there. I'm guessing, but so here is your low density, and there's a coexistence, and there's a high density phase on the right. Perhaps I've got it wrong. Does somebody know? Low is on the left. Okay, so there we are. Good. All right, so these are the profiles here. What about this maximal current phase? Well, that's the one which corresponds to this picture. Okay, and as you can see, it's where the two roots coincide. They can coincide if C is 1/4, square root goes away, and the density is half. So all throughout this phase, the density is actually a half. Where is it? Except that the approach to half is particularly slow on the two sides. But the bulk density is a half, and the current is 1/4. This is the largest current you could have. Okay, so I will perhaps stop with this description of the phase diagram. Here are the phases 1, 2, 3, and one line of coexistence. So we can put that down, coexistence. With each, there's actually a bulk profile which is qualitatively different from bulk profiles in the other phases, in this sense. And the way to find these within the mean field theory is to just do these iterations. Actually, if you have not done iterations before in any problem, just do it on a calculator. I mean, earlier we used to do it on calculators. It's a lot of fun. Yeah. Okay.
The other problem is give 3/4 to the all three children and let suppose give 1/4 to the fourth one.
Nothing like that. So
Okay. No, you give, there are 3 remaining quarters. You give it to the 3, and each of these 1/4 of there to the fourth one. That will be your yeah. So you always have the same shape.
They will? Okay, you show us in the end. But now please concentrate on the phase diagram. Right? Yeah? Okay. Speaking of calculators, the other day, just before I left, Kedar Ramle, who's one of my colleagues, comes to me. I'm regarded as very old. Do you actually have a hand calculator which I can? So I said, telephones nowadays have, he wanted a real calculator with buttons. So I had to disappoint him, but I said, I have a slide rule. He quickly ran back. He didn't want a slide rule. How many of you have used a slide rule? Huh? Very bad. What about log tables? Oh, that's very good. Log table is good. Okay, good. Slide rules are based on logs. In fact, it's a good project. Make your own slide rule, which at least is correct to the nearest integer or something. I mean, up to 100. Okay. Anyway, now, all right. Now, before I leave this, since there's an exact solution available, I should put it down for the record. So here you are. This is an exact solution for tau k, kth site, the average tk, exact. Tk is equal to, okay, get ready, half plus 1/4. There's no series or anything, it's just factorials. Okay, so here we are. 2k factorial, n factorial squared. N is the same as what we used to call L. 2n minus 2k plus 2 factorial divided by k factorial squared, 2n plus 1 factorial, n minus k plus 1 squared, the whole thing multiplied by n minus 2k plus 1. Now, in which phase is this? I've forgotten, but the main thing I wanted to convey is this is a formula which you could not have guessed very easily. So how is it presented in the paper? It's presented as the result of a calculation based on some special matrix algebra which is introduced for this problem. But what made the authors think of that matrix algebra? See, this is very important. You have to understand the workings of the minds of the people who write the papers. Fortunately, they've told us, so I'll read out. This expression is the main result derived in the present paper. The initial method used to obtain it had nothing to do with the above derivation. So before this, they have given you a derivation of this. They have not done it this way. It was first obtained, there's a lesson here, please do this. Was first obtained by solving exactly the problem on a computer for small sizes, n less than or equal to 10. So they took the problem, they solved it exactly. Master equation, do it. Diagonalize the full master equation. By looking at the numerical results, it appeared that some of the TIs were very simple rational numbers. And then this formula was first obtained by trying to find an expression which would agree with those numerical results. It is only after this formula had been guessed as a conjecture that the above method was developed to demonstrate its validity. This is actually important, and remember this in your lives, which go ahead. It helps to know the answer before you attempt a proof. It's not always easy to find the answer, but try to do it in some way or the other. One thing is you can guess. And that's always useful, because as you attempt proofs, you'll usually find a proof that your guess was wrong. But keep doing it, and sometimes use numerical methods. And this exact or something or the other, even Monte Carlo, you do something and you get some funny oscillations and correlation functions. That tells you something is happening with something going around, maybe a kinematic wave or something, So numerical results are useful, but use them to try to prove things. This is a wonderful example, and it's very nice that the authors have stated it. As a fit to the numerical results. Yeah. So they must have had quite a few answers for various n's and k's, and certainly they must have noticed fractions like 5/8. You don't get rational numbers very easily, and yeah, in the past, this approach is really very fruitful. Do something and work hard. I mean, keep thinking about it, even all the time. Yeah, no, it does. So this is at a particular value of alpha or beta, which I have forgotten. I mean, it's okay. So I didn't look it up because this was not the. Okay, so it goes on and on. So somewhere right in the beginning, they must have said for this alpha and beta, capital T. Maybe it's alpha equal to beta equal to no. Okay, I can't find it quickly. You're welcome to have a look at the paper, but yes. The which? T versus I. Yeah, this? This. Yeah, it should. Thank you. You're right. Very good. That's a very good observation. It should not go below T minus. Otherwise, yeah, should start somewhere there. That's right. Thank you. Okay. Good. So I'll leave this topic now. We'll come back to our other comments on KPZ, and I think we will run out of time then. Okay. Shall I rub this out now? Yeah. Okay, so yesterday we were at this stage that we were looking at the Edwards-Wilkinson equation. We had actually looked at it, and then we looked at the engineering dimension type scaling, and we saw some answers there. So just to remind you, oh, I've lost that sheet. Okay, so let me use this one. So we are discussing in general, the KPZ equation. So let me make a few remarks also, and we'll proceed at a slightly cracking rate so that we finish. And I'm not sure whether the half is traditionally put or not, is it? Now, suppose you were to write it, would you put half?
Yes.
Okay, good. So then we're in good company. All right. So now the Edwards-Wilkinson equation is gotten by dropping some terms, and that is d d2h dx squared plus the noise. You remember this. This is a linear equation, immediately solvable because it's linear. You see, some people are smiling, but okay, very good. Nice. So, 1. We worked out the correlation function h f x n t and h0 0, and we found that it is given by 1 over 2, okay, 2 gamma by d, 1 over 2 pi integral dk over k squared 1 minus e to the minus dk squared t plus ikx. We noted that sigma squared, and here I think I made an error in writing things yesterday, just correct it please, varies as x. So this is the definition of sigma squared. X to the power 2 chi. I forgot the 2 when I wrote it. If t equals 0, it varies as time to the power 2 beta if x is 0. And overall, there's a nice scaling description, scaling function of x and t, which says that this is equal to a constant, non-universal constant capital A, followed by x to the, I guess if you are writing it for sigma, then it's x to the chi, okay, times a universal function of t x to the z, and to make it universal you may have to put in a non-universal constant c here, and this was the answer, right? And then we worked out what capital Y had to do in order to be consistent with these two limiting forms. And then as a result we deduced from scaling that beta has to be equal to chi over z, roughness exponent divided by dynamical exponent. And given that in this problem chi was half, which we had proved anyway earlier but also re-derived, z equals 2, so beta was 1/4. And I made the remark, and I won't go beyond the remark very much, to say that this quarter is related to the fluctuations of a single particle, a tagged particle in the symmetric exclusion process. Okay. And then we had this question which I had posed, how can it be that a single particle which is hemmed in by neighbors and at a given separation, how can that even increase, maybe slower than t to the half, but how can it increase indefinitely, t to the quarter? And I just want to give you the rough answer. This hemming in argument is correct, you are caged in, but what that means is that if you look at the coordinate of the ith particle and compare it to the coordinate of the one in front, and you look at how this as a function of time changes in compared to 0, if you look at the mean separation squared, that does not diverge, that approaches a constant. But average x squared actually does. I mean, and the reason is that a lot of particles, bunches, move more or less together, but they move, preserving nearest neighbor and next neighbor, distances don't get too big, but the excursions are unbounded of all this full bunch. So that is the way to understand it physically. Since I posed this question, I thought I should answer it. Okay. Now, one other remark I wanted to make. This is, of course, easily generalizable to higher dimensions, like 2 dimensions, this whole calculation, though we didn't do it, but it's easy to do. The answer is that the surface is logarithmically rough there, and you can work things out. One point I wanted to make. Of course, we've dropped the nonlinear term, but we've also dropped this term, c dh by dx. We've dropped it on good grounds. We have done a Galilean shift and removed it. We can do it, nothing wrong. Suppose we had not dropped it. Okay, what would it mean? It would still be a linear equation possible to solve. What would the answers be? Well, in that case, what you'll find if you just do the calculation is that beta is a half. If you fix yourself at one spot and you ask how do the height fluctuations vary at that spot as a function of time, they vary as time to the half, not time to the quarter. Why is that? So I just wanted to quickly tell you the answer. The reason is because there is a kinematic wave. You have not kept up with it. Therefore, at that fixed space site, that wave is coming past. What you are sensing, therefore, is the spatial correlations in the wave, because at time t, that part of the wave will be here. Okay? And the spatial correlations, in fact, grow like x to the half. So convert x into time, x over c. X over c will be a time, and x over c to the half will, okay. Or if you want to ask the question in the other way, at a given time, that part of the wave which was a distance ct away will be here now, and that would be, okay. So that's a qualitative reasoning there, but the calculation will show this. So, and of course that's okay, you are sensing the sliding of the wave. But if you want to sense the dissipation, you'd better move with the wave. This is the intuition there. All right, good. Now, what we further did is we analyzed quickly what happens when you change length scales by a factor b. What happens to the equations. And unfortunately, I don't have that sheet very handy, but let me find it because I'll be... Yeah. Okay, so for instance, we found that, since we've gone through it, is it okay if I don't repeat it? Have you all noted it down yesterday, for the Edwards-Wilkinson problem? And by insisting that the system of equations be scale invariant. So what we had done is that x went to bx, time went to b to the z times time, and the field itself h went into b to the chi times h, and then we insisted on that, and we read off one by one the exponents. So what we had is, so what we implies for the Edwards-Wilkinson problem, z equals 2 and chi equal to, so invariance under this. Under this implies this, and chi equal to z minus d over 2 So, in 2D in particular, chi is 0, but we have a logarithmic roughening. And as I said, like in the 3D Ising model, where the interface is a 2D sheet, above the roughening transition temperature, I believe these things are more or less consistent with numerics. Okay, but now suppose we come back and say enough about the linear problem. Let's come back to KPZ. What can we say? And this is what I wanted to address in the remaining time. The first thing is that we've seen already that we can get somewhere with this scaling business of the dimensions here. I mean, so we can ask what happens to dH by dx the whole squared under this same transformation, and what we find is that you know so let me write the equation in this form. The rescaled equation doing this length scale transformation is d b raised to z minus 2 d2h by dx squared. I am removing the c term, plus b raised to z minus d by 2 plus chi times eta. These were the old terms, and now you have a new term, half lambda times b raised to chi plus z minus 2 dH by dx squared. Okay. So, let us say we are in one dimension, specialized to dimension 1, where we know that and let us say we are close to, or we are essentially at the linear fixed point. So, we have the Edwards-Wilkinson problem and we put on a very small value of lambda. All we want to know is whether that will grow or get smaller under this B transformation. So, we already know Z is 2, chi is half. So, we can substitute here. What will we get? 2 minus 2 is 0. This is b to the half. Since b is large and getting larger, this will get very big, no matter how small lambda is. So, what it says is that this perturbation is relevant. The linear theory will not be, will be changed. It will not be valid the moment you have lambda, no matter how small. And in fact, the moment you have lambda, you have the KPZ theory. So is there any way to find the KPZ exponents? Well, there is. The first thing is you can appeal to the exclusion process. We have an exact mapping between the lattice model for the interface and the exclusion process, and we can try to see what we can say about the W matrix in the exclusion process through other many-body techniques. The first person to do this was in fact present here last week. So, you had a very distinguished set of lecturers last week. Not to say not this week. So, this was Deepak Dhar. So, he was the first to actually crack this problem. Unfortunately, he didn't write a long paper. He wrote an abstract and he announced the result, and that too in a journal which is there but not read very often. It's called Phase Transitions. It's a good journal, by the way. So there the answer was announced that Z is equal to 3 by 2. Actually, the Z equal to 3 by 2 was also suggested by Cardad, Parisi and Zhang in terms of an approximate renormalization argument, which was approximate. But this was an exact result. It was based on Bethe ansatz. 2 years later, I think, Gua and Spohn, in fact, worked things out again, and they wrote a longer paper where they explained how this Z equal to 3 by 2 arises. And by the way, it arises in the way to get it is what you all have done in your homework problem. You have to analyze the spectra of eigenvalues of the W matrix and see where the lowest one is compared to the 0 eigenvalue which corresponds to steady state. In the single particle on a ring, we found that that's L squared, 1 over L squared is the gap. In this case, you can show that it is 1 over L to the 3 by 2, and that leads to Z equal to 3 by 2. Okay. All right. So this is the, so we know the answer 3 by 2, but we are not in a position, especially now, or even given a 1 week, we may not be in a position to go through that solution. But what we will do is we will somehow give an argument for why Z is 3 by 2. Now, this argument is actually takes me to this point, the correspondence between KPZ and the Burger's equation. Okay, so let me first of all write the Burger's equation so that you will all remember what it is. It's an equation for the velocity field in a fluid. Where am I? Okay, so here let me write it. So dV, V is a vector in any dimension, so I'm writing dV by dt plus V dot grad V. By the way, you recognize this plus that is actually what is often called capital D by dt. What is the word for that? Convective derivative. That's right. So this is d by dt of V, where if you're imagining a fluid element that's carried along by the velocity V, I mean, this is the derivative. It tells you about the change of that element, you know. Anyway, d by dt of this there's a viscosity, and let's say there's noise. In the standard Burger's equation, there is no noise, but we're considering the noisy Burger's equation. It's called that. Okay, where it will have the usual properties. Okay. Now, what is the correspondence to KPZ? That is very immediate. Please do it in 5 minutes later. And that is, take the KPZ equation, operate grad on H, and define that to be V. And you'll find that this equation is obtained if lambda is equal to 1. Okay. So this is, so gives that with lambda equal to 1. So in some sense, there's an assumption. For the moment, we'll make it. We'll later show you how to get rid of it, no matter what lambda is. But suppose lambda is 1. It's a nice value. I mean, it's not like 0 or something. It's 1. It's a typical KPZ value. But the other thing is, we have actually, so given KPZ, we can always do this. But given V, can we always do that? Answer is no. You can do this provided you don't have vortices. So this is a vortex-free flow. But it's all right. It's an important sector even for the Burger's equation. So we're justified in thinking about it. Now, Burger's fluid velocity. What does that remind you of? Galilean shift. That is what it should remind you. Now, suppose you have a fluid, infinite fluid, and you do a Galilean shift. Should your equations remain valid after Galilean shift? Do Newton's laws remain valid under Galilean shift? Yes. These are ultimately derived from essentially Newton's laws. I mean, the fluid equations of fluid mechanics, Newton's laws, and if you like, I mean, continuity equation and things like that. So this equation must be invariant under Galilean shift. So let us see what we are demanding. We are demanding that if we take the velocity and we apply a Galilean shift by an amount V naught, okay, and we have resultingly a velocity which we'll call V prime in that frame. The important thing is that this V prime is a function of a new coordinate in that shifted frame. In other words, the Galilean shift will affect not only the velocity, which is the thing you're looking at, but also the underlying space, x. Okay. So x minus V naught t, t. Okay. Again, Without proof, I will assert, well, actually almost with proof, sorry. Okay, all right. So now what have we said? We've said we have a fluid and we've done a Galilean shift, and the equation should be invariant. In other words, the equation for V prime should be the same as V written in terms of x prime now. Okay. Now we come along and we say, okay, but we want to do more. We want to do scale transformations, which is another sort of transformation. It's not Galilean, it's something else. So we put in this factor B, we do everything, and in particular we'll end up with terms like that. Okay. Suppose we had done it at the level of this equation, V rather than H. We would have gotten something there, except that this, since lambda would have sat here, this is the nonlinear term, you would have gotten this b to the power. But suppose we demand that even under scale invariance, we want the same equation back. It's a demand. It's a very reasonable demand, because Galilean invariance is a very, what's the word, fundamental demand. But we are making a demand, and that demand will then give you an equation. This is equal to 0. So Galilean invariance, to be preserved under scale transformation, that demand implies chi plus z equal to 2. That is the only way you can have it. Okay. If you do the renormalization calculations which Kardar and company have done, in fact you find that, okay, well, so let me not. So if you make this demand, now you can read off what z is in one dimension. In one dimension, we've already shown, and this we have proved because of the product measure of the ASEP, that chi is half. So z is 2 minus chi, so z is equal to 3 by 2. Well, and it's actually correct, as confirmed by calculations which don't rely on this, and it seems to give you a good way to understand the answer. So I'm afraid I'm going to leave it at that spot, but at least then we have the 3 kpz exponents. What about beta? Well, beta fortunately is given by the ratio of chi to z. So what will it be? It will be half divided by 3 by 2. So that will be 1/3. That is correct. So these are your kpz exponents. Now, what else did I want to say? Yeah. Now, I did want to discuss the behavior of the kpz equation as a function of dimension. Unfortunately, I don't know the exact answer very, very well. So I'll say something, and somebody who knows better should correct me, because I'm not 100% sure that what I'm saying is right. Yeah. So, but let me say what I know, or what I think I know. Okay, this correspondence to directed polymers in a random environment we may not be able to get to. Read it in Medina, etc. This is a very nice correspondence to the problem of a directed polymer, meaning it's sort of stretched out in space. Okay, there's no time yet, and there's the polymer, and there's a random environment. See, normally a polymer will like to do something that will maximize its entropy, but given that there's a random environment where the energy can be lowered by taking advantage of some spots over others, the polymer will do something unusual. And that is described actually by this kpz theory. There's an exact correspondence. But we won't enter into that right now. Okay, good. So let me summarize what I think I know, or what I think is the case for the higher dimensional kpz. Okay, so this is as a result of a perturbative renormalization group for the nonlinear term. Okay, so we keep some. So let me just quote the answer. This is the answer from some such calculation. Let me define a parameter little g, which is lambda squared d divided by nu cubed, some combination of the coupling constants, and ask how does this change under length rescaling. So this is the typical question one asks under a normalization, right? So what do you do in a renormalization group calculation? You change the length scale, effective length scale, which is tantamount to doing something in momentum space, integrating out large momenta, and see what the effect is on the coupling constants that remain. And that gives you a recursion. Have you, any of you studied renormalization group or done some calculations of this sort? 1, 2, 3, 4. Okay, well, all right. I mean, organizers, maybe next year you can think of a renormalization group. No? This year? Yeah. No, I think this is an important body of knowledge. Okay, if I could take 1 minute off to say something away from the class, which I've been doing all the time. So, no, as students of statistical physics should in their lifetime, not full, as students or perhaps first year postdocs or second year postdocs, work out 2 things on their own or with, you all can sit together. You can sit in a bunch and work it out, but work out every step. 2 things. One is the solution of the 2-dimensionalizing model. The partition, at least the partition function, never mind the magnetization, that is difficult. Free energy. There's a beautiful paper by Lieb, Schulz and Mattis, which gives you a very simple way to approach the problem. Study it, approach it, and work out the solution. That is number 1. Number 2, work out the first order in epsilon of the epsilon expansion, which is an expansion around 4 dimensions for, let's say, the simple Ising model. I mean, 5/4 field theory as it's called, but just work this out to first order in epsilon. It's not very difficult. There's again a beautiful article by Ken Wilson in the 1972 or 70. I mean, but Wilson and Kogut actually it's called. But I'm sure there are very good accounts of it by now in textbooks. I mean, I was a student in the 1970s, so I actually read that article. But where can one read this now? Epsilon expansion. What would you advise? There may be better textbooks. There are many books, but you can talk to our colleagues here. Yes. Wilson and Kogut, about 1972. Physics reports. Okay. All right. Anyway, but here is the result of a renormalization group calculation for this problem. And what it tells you is the way the coupling constant G varies as you change the length scale. Little l is the same as little b earlier. So this is, here is the answer, 2 minus d over 2 times little g plus a constant, which depends on dimension, but strictly positive constant, 2d minus 3 over 4d times g cubed. And then there are higher order terms, but this is what is computed. Okay. Now, what do we find? Okay, so basically what you have to do is look for fixed points of this equation, and you find that there are 2 fixed points. Okay, and then you can ask near one fixed point, if you make a small deviation, will it grow or will it shrink? So based on that, you get the following. I won't draw dg by dl, etc. I'll just draw a schematic line. So here is your Edwards-Wilkinson fixed point. Here is some other fixed point, and I'm putting the picture for d equal to 1. Then this calculation suggests, gives you that this is unstable with respect to that, and this is the direction of the flow, which is exactly what was suggested also by our substitution here, that the perturbation will grow. And here's, however, another new fixed point with the exponents that we had, which I rubbed out, which will govern what is happening here. What about d bigger than 2? Okay. D less than 2, I mean if you can imagine some dimension between 1 and 2 will be similar. D bigger than 2 on the other hand, the Edwards-Wilkinson, so there are 2 fixed points again that you find in this calculation, but this is the other way around, which in some sense is good news. It says that what you get from the linear theory will at least be valid provided your nonlinearity is not too large. I mean, so right, this is all obtained on the basis of perturbation theory in G. But if it is large, well, this fixed point is actually unstable and it leads out. The question is, where does it lead out? And it's, so this is the point I am not 200% sure of. There is another fixed point perhaps, which I will call the strong coupling KPZ fixed point, where this goes, and which is, seems to me, outside the reach of a perturbative theory here, because there is another fixed point in between. So this can't be handled there. And this is my understanding of what it is, but I am subject to correction. So I know it does not jive with what Manas has been telling me, but this is what I thought it is. So I thought I should say. Do you have any comment? Not at the moment. Okay. All right. We can, I mean, a more careful reading of the literature is what I should have done. I didn't do it. I apologize for that, but read and find out. Okay. So I think it's time. It's time to stop.